So section 5.4 has just a couple, I think, pretty simple formulas for us to use. We bring up some old notations and make sure we're still comfortable with those, meaning like n is the number of trials. We're dealing with a binomial, so that's a set number of trials. P is the probability of success. Q is the probability of failure. Okay. We had the binomial formula. Which we use if I want the probability of x equal to some amount. And we use NCK, so that's basically the number of ways we can arrange that success is in there, times the probability of success to the k times the probability of failure to the n minus k, or we use binom PDF with n, p, k. So either of those will give us the same thing. But what I'm doing here is I want to figure out kind of what the mean and the variance and the standard deviation so that we can kind of do some normal approximations with this later on. Think about it this way. I'm going to come up with a pretty basic example. If we have, let's say, a 5-question test, it's multiple choice, with options A through E. A, B, C, D, E. Yeah. So you're guessing on this because I'm not going to give you the test. You're just going to guess the answers, right? What is your probability of success? What's the probability of you getting a correct answer? Well, there's 5 options, right? A through E, and only one of them is right. So that would be 1 out of 5. Here, in fact, I'm going to change this up just a little bit just to make things a little more crazy. Call it a 10-question test, okay? So 10-question test, multiple choice A through E, gives us 5 options. So if I'm guessing, the probability of getting one right would be 1 out of 5. You with me? What the average is they say, well, out of a 10-question test, on average, how many would I expect to get right? Some of you are like, well, 2. Some of you are like, how do they know 2? Well, look, if I have a probability of getting 1 out of every 5 right, then that means out of every 5 questions, I'd expect, on average, to get 1 right. Does that mean I'm going to for sure? No. But on average, right? So out of 10 questions, I'd expect to get 2 right. That's this mean. That's this n 10 times p 1/5. If I take the probability and times n, I figure out on average, I expect to get 2 questions right. The standard deviation is where I take that n times p times q. Well, if the probability of getting one right is 1/5, the probability of getting one wrong is 4/5. Right? The other 4 answers are right. Now keep in mind this is not standard deviation because of all the stuff we do with this, we need to make sure we square root all of that. Okay? So what I'm going to do is I'm going to go ahead and run this actually real quick in the calculator. Do about the square root of 10 times 1/5, which would be 0.2, times 4/5, which would be 0.8. And so we have 1.26491. 1.26491. This is just using a formula to get these. I want to make sure that we understand using the idea from 5.2 and 5.3 how this still works, and I can do this again in the calculator. So real quick, I'm going to do a review of stuff we did in 5.2 and 5.1, which is to say, if I wanted a list of all the probabilities, if I wanted to make a table, we've done this before, I could go to the menu, statistics, we're doing distributions all the way down, binom, PDF. How many trials do we have? Well, there's 10 questions. What's the probability of success? Well, 1 out of every 5, or 0.2. And what if I leave this blank, right? Then what it will do is it will fill in and make a table of all of the probabilities. This is the probability I get none right, 1 right, 2 right, 3 right, and so on and so forth. Okay? So, that's something we've done before. If I leave that blank, it creates the table here, right? I'm actually going to do this, but I'm going to do it in this table. So here, these are going to be our x's, which, right, how many successful questions can we have? From 0 all the way up to, hypothetically, I could get all 10 right? What I'm going to do on the right one is I'm going to get those probabilities. So the way I'm going to do that is in the menu, statistics, distributions, all the way down to binomial PDF. We have 10 trials. Our probability of success is 0.2. And the x values, this time rather than leaving them blank, I'm going to say fill in everything from A. Where'd my brackets go? A bracket. There we go. So it will do binomial PDF on 10.20, 10.21, 10.2, all the numbers from A. And if I hit enter here, so just make sure 10.2A, it fills in this table. Those are the same numbers, 0.107, 0.268. Those are the same numbers we had here. It's just now in a nice table form, okay? So in 5.2, this is what we would call a distribution of frequencies, or of probability distribution, sorry. We can find the mean and the standard deviation of all these. Every x times its probability added up, right? And all those different formulas, or let's keep it simple. This is something I encourage you to know for the upcoming test. Statistics, calculations, one variable stats. It's like, well, I have two lists. Well, not really. I have an x and a probability that go together, where the x was in A, and the B was really our frequency. And so that's where you do A, B. And this is something we used in 5.2. But I can do that here also if I have any probability distribution. I can do it on the x's, the probabilities. And what's nice is what? It gives me the mean. And it gives me, you got to scroll down, the standard deviation. What was our mean that we had? Well, we said 1/5 times 10 is 2. And we said the standard deviation, 1.26491. 1.26491. So these formulas, when I have, and keep in mind, this is only for a binomial distribution, I can get these numbers really quickly using these formulas. Okay? It's nice to see how it works, but so what are we going to do? Remember round off rules, be careful with that. So just be careful, I would say. We generally round to 3 decimal places, but don't do that till the end. Keep as many as you can. It says keep one more. I mean, I would keep 4, 5, 6, keep as many as you can until the very end. Range rule of thumb. This we've talked about before. When is something considered unusual? Well, we said it's unusual if it's less than 5% probability or more than 2 standard deviations away. So this is basically what we can say. The mean minus 2 standard deviations. If something is less than that, is unusual. If it's less than the mean minus 2 standard deviations, or it's unusual if it's greater than the mean plus 2 standard deviations. So if you're outside of that, okay? So let's apply this. 40% of the population has brown eyes, right? What is that 40%? We're calling brown eyes a success. Sorry for all you blues and greens, and this is success, right? Groups of 600 people are randomly selected. Find the mean and standard deviation. Well, what does the mean mean? Well, out of 600 people, and this is key, I will use this phrase instead of mean sometimes. We say, what is the expected value? Well, if 40%, right, have brown eyes, then I would expect 40 out of every 100, or 40% of the 600. That is n times p. So that should be, what, 24? Standard deviation. Well, that is just n. times P times Q. What's Q? Complement of P. So 0.6. Now that's not going to be our answer. To get standard deviation, we're still going to have to square root that. But I'm just going to run this in my calculator, okay? So, let's see, the square root of 600 times 0.4 times 0.6. 12. Did I do square root on that already? Something seems off for me. Give me a second. That's, wait, yeah, 40. Yeah, see, and I'm hoping some of you are screaming at your calculator because I'm like, that is not right. 0.4 times 600 would be 240, so that's what makes a little more sense. So be careful with that. And then this ends up being the square root of 144, which is just 12, okay? So really just running these formulas in your calculator. Use the range rule of thumb to identify what would be unusual out of 600 people, right? Well, it would be the mean minus 2 standard deviations, so it would be 240 minus 2 times 12, 240 minus 24, or 216. So anything less than that would be unusual. Or the mean plus 2 standard deviations, 240 plus 24, so 264, 4. Anything greater than that would be unusual. So then it says, is 200 unusual? Oh wait, real quick. It says, what would be usual, right? The usual, what I would expect to see, would be anything between 216 and 264. So the usual would be between the 216 up to and including the 264. Unusual would be anything below the 216 or past the 264, right? So then it says, is 200 usual or unusual? Well, it's outside of this range, and it's unusually below, so it's unusually low. All right, we're almost done with chapter 5. This should not be the hardest thing we do here. So 10% of us are left-handed, right? If 3 people are randomly selected, find the probability they're all left-handed. Well, we have a set number of trials. We have a probability of success, and we want all left-handed. So that means probability that x is equal to 3. We have 3 left-handed people, right? I can use the formula. 3, choose 3, 0.10 to the third, 0.9 to the 0, or I can use binomial PDF N P K. So I'm going to use the second one, right? So binomial PDF, statistics, distributions, and we have 3 people, probability of 0.1, and we're interested in all 3, right? So 0.001, not terribly likely, 1, what is that, thousandth, or 0.1%. If 3 people are randomly selected, find the probability that at least one of them is left-handed. Well, what does that mean, right? At least one means 1 or 2 or 3. That would be binomial CDF and what we would have is N or P. At least 1 means what? From 1 up to 3. So binomial statistics, distributions, binomial CDF this time. 3.1, and we're going from 1 to 3. 0.271. Okay, So this was the probability that x equaled 3. This was the probability that this was at least 1 greater than or equal to 1. Okay? Now it says, what if 50 groups of people were randomly selected? What would we expect on average? Well, if 50 people were randomly selected, and there's a 10%, I'm sorry, was it 10%? Yeah, 10% probability of left-handed. Okay? Then on average, and here's the key word, what was the mean number, standard deviation? Oh, I didn't use it, but the idea is the mean is the expected. Okay? We would expect n 50 times p. We would expect 5 left-handed people. Does that mean that's always going to happen? No. There's going to be a standard deviation to that of n times p times q. So I don't know what the square root of 4.5 is. So let's go ahead and do square root of 50 times 0.1 times 0.9. So 2.1213, 2.121. Use the range rule of thumb. Would it be unusual to get 8 left-handed people? Well, what would our lower unusual be? Well, less than the mean, minus 2 standard deviations, less than 5, minus 2 times 2.121. 5 minus 2 of these messes, and not 22, 2 times. That looks better, except it's divide, times. So 0.757. Or the mean plus 2 standard deviations, 5 plus 2 times 2.121 should be 9.242. So anything greater than that would be unusual. Is 8 unusual? Well, this says we can expect it to range between, well, a little less than 1 and about 9 people, right? Is 8 in that range? So this would be our usual range, would go from 0.75, which you can't have 0.757 people, so about 1 people, up to about 9.2. You can't have 9.2 people, so about 9. And 8 is in that range, so 8 would not be unusual. The Helsinki Heart Study asked whether anti-cholesterol drug gemfibrozil, yes, I'm sure I said that right, reduces heart attacks. In planning such an experiment, researchers must be confident or that they're large enough. They plan to give that horrible name thing to about 2,000 men and a placebo to the other 2,000. The probability of a heart attack during the 5-year period is about 0.04. So if the probability of a heart attack is 0.04, then out of 2,000 men, how many would we expect to have a heart attack? Well, n times p. That should be, I think, 80. On average, we would expect 80 heart attacks. Does that mean that's always going to happen? No. There's going to be kind of a lower and an upper bound unusual, right? So the lower bound, well, I got to get the standard deviation first, would be 0.4 times 0.6. So it should be 6 point something. Let's double check that. 2,000 times 0.4 times 0.6. Oh man, I was off on that. So 21.9. Okay. So it seems off on that. Let me double check again. 2,000 times 0.4 I keep doing that, would be 800 Gs. That's why. Let me go back. Or is it? I gotta be more careful. What is it? 0.04. That's why. So it's 0.04. Hopefully you're screaming at your computer. 0.96. All right. So 0.04 would be 80. So that was right. Good. Let's fix it in the calculator. So the square root of 2,000 times 0.04 times 0.96. So what is that? Yeah, 8.76. That makes more sense. So on average, what would we expect, right, if with 2,000 men? Well, lower would be 80 minus 2 times the standard deviation. So 80 minus 2 times this would be about 62.5, 62.47 heart attacks. Anything below that, right, we're going, man, this medicine's awesome. So if we gave people this medicine and there was like 60 heart attacks, or 58 or 57 or anything less than this, we would be unusually low. We'd be like, man, this medicine is awesome. It is reducing the number of heart attacks. It's significantly below what we would expect. What would the upper mean? Well, that would be 80 plus 2 times 8.76. So that would be 97.52. So if I'm giving the people the medicine and they have 90 heart attacks, right? Well, that's still within the usual. That just means the medicine sucks, doesn't work. But if I give them the medicine and you have 98 heart attacks, 99, 100 heart attacks, then you go, not only does this medicine not help it, but it's actually causing more heart attacks than we would expect. Okay? So that's what we're doing here. If we are, with this medicine, if we are below the average, okay, then basically the medicine works. Hooray! We help people, we make millions of dollars. If we are above average, then this is a medicine that kills people. Please be careful. Don't use this medicine, right? All right. So that's it on this. So go ahead and should be, like I said, a pretty easy ending for Chapter 5. Keep up the hard work.